Hello, hello. We will be once again starting from the topic of two element solution. This is because one of the term in the elemental equations has been repeated. Let me brush through the topics which have been dealt in this particular heading. So we had our domain consisting of node 1 and node 2. And the unknowns are indicated by UA and UB. The boundary terms are the known values of the parameter u at x is equal to 1 and any other point. And similarly, since we are taking a linear element, the expression for the parameter is given by u is equal to phi1 a1 plus phi2 a2, where phi1 and phi2 are obviously linear polynomials given by expressions on display. Now, with the help of this, the stiffness equations for the linear elements are going to be represented by equation number one. And obviously, there are two unknowns given by A1 and A2, which happen to be the nodal value of parameter. Uh, they have been represented by A1 and A2. Since there are two unknowns, therefore we have two equations. We are going to require two linear simultaneous equations for finding the value of A1 and A2. Now, kindly notice that on the right hand side, there happen to be two terms. One of the term is a boundary term, which is the second term on the right. The other term represents the load on the element itself. In fact, this is the result of the integration which has been carried out over the entire domain. This is the first term on the right of the equality sign. In fact, this is the very term which has been missed out in the development of the two elemental solution which we have done in the yesterday class. So just for the continuity sake, just for the sake of completeness, we are quickly brushing through the entire development of two element solution. Then we have the domain divided into two elements, node number 1, node number 2, and node number 3 located at XA, XB, and XC. Element number 1 is going to comprise of node 1 to node 3, and the element number 2 is going to comprise of length between node 3 to node 2. Kindly notice that both the elements happen to be linear element. They are of equal length also, but in reality, if we take any combination of elements, there might be a linear element working in the conjunction with a quadratic element and things like that. And also, there is no requirement, there is no compulsion that the length of both the elements has to be same. What I want to say is that you can use any combination of elements with any length which might suit you. And then the expression of the linear polynomial is linear. The expression of the unknown parameter is linear for element number one, and the unknown parameter for element number two are on display. Similarly, the unknown parameter is represented by u2 is equal to phi3a3 plus phi4a4 as is in the equation on display. And phi3 and phi4 are also have been illustrated. The thing is that despite of the fact that the domain has been broken down into number of elements, the boundary condition are going to remain same as in the one element solution. The boundary condition are the known value of unknown parameter at x is equal to 1 and the flux at x is equal to 2 as we have seen in the previous slide. The next slide deals with the concept of continuity. Obviously, because the domain has been broken down into a number of elements, you will require the unknown parameter between the two elements. So this is going to place some constraints on the type of and at this particular point we derived two types of we gave two types of examples. One was the C naught function. If the function happens to be continuous, it is of class C naught. But if the function itself, along with the first derivative, is continuous, it belongs to a class C1. This is what we have done in the previous class, so I will not repeat it here. And then we have divided the domain into two elements. Element number 1 comprises of node 1 and node 2 located at XA and XC. Similarly, element number 2 comprises of node 3 and node 4. These nodes are located at A3 and A4. Similarly, for the first element, the unknown parameter is given by the expression u is equal to a1 phi1 plus a2 phi2, where the phi1 and phi2 are given by expressions on display. Similarly, for the second element, u is given by a3 phi3 plus a4 phi4, where the values of phi3 and phi4 are given by the linear expressions in X. Then coming to the boundary terms, obviously they are the same which have been derived previously. Now the thing is, since we have already derived the stiffness equation for a case where the entire domain was represented by a single element on display at the moment, when we divide the domain into two elements, we basically are going to use the same elemental equations which we have derived earlier, but are simply going to replace some nodal values, such as when we are talking about element number 1, we are simply going to replace xb with respect to xc. Similarly, when we are talking about the stiffness equations of element number 2, we are going to replace xa and xc to get the stiffness equation of element number 2. So for element number 1 gives us these equation for node 1 and node 2. Similar expressions are going to be obtained for element number 2, which comprises of node 3 and node 4. So in total, we get four equations. Two equations for element number 1. The unknown parameter happen to be A1 and A2 for equations of element number 1. And similarly, we get two equations for element number 2. The unknown parameters are represented by A3 and A4. So in the next slide, we are going to see all the four equations clubbed together. So these are the two equations of element number 1, and this is the two equations of element number 2. We get two linear simultaneous equations. So the local stiffness matrix is a square matrix of size 2 by 2 for both the elements. And on the right hand side, we have two terms. One term, which is the first term on the right, represents uh, the loading done on the element, while the other term, which is boundary term, which has to be evaluated at the uh, endpoints of the element. Now substituting the value of nodal locations, that is XA, XB, and XC, we get we get the four equations for element number 2. And in the next slide, we are going to keep all the four equations in a single matrix form. This is the form I'm talking about. So since the equations for the first element, they are they contain terms such as a1 and a2. They do not contain terms of a3 and a4. Therefore, we have four zeros appearing um, in the equations of the first element. And similarly, when we talk about the um, third and the fourth equation for the second element, that is, these two equations depend upon a3 and a4. That is, they do not depend upon a1 and a2. Therefore, the coefficients of a1 and a2 are 0 in the third and the fourth equation. And similarly, there are some terms representing the loading, that is the first term on the right, and some terms representing the uh, flux, that is the second term on the right hand side. So kindly note, but the flux has been evaluated at x is equal to 1 and x is equal to 3 by 2 for element number 1, and it has been evaluated at x is equal to 3 by 2 and x is equal to 2 for element number 2, which means that the flux is evaluated at x is equal to 3 by 2 for element number 1 also, and it has also been evaluated at the same point, same location for element number 2 also. Now after this, we are going to talk about the continuity condition. Since both the two elements have actually a node in common, node number 2 and node number 3 actually are a same node that is located at xc. So obviously the value of the unknown parameter is going to be same at both these 2 points, which gives us a constraint equation of the type that u1 at 3 by 2 is equal to u2 at 3 by 2, which means that the value of the unknown parameter at location 3 by 2 for element number 1 is equal to the value of the unknown parameter for element number 2 at location 3 by 2. So when you apply this particular constraint equation to the trial function of two of the two elements, you basically get a constraint equation of the type a2 is equal to a3. This basically has been derived because the shape function of the two element satisfies some conditions at the endpoints, such as phi 1 is 0 and phi 2 is 1 at x is equal to 3 by 2 for the first element. Similarly, when you talk about the second element, phi 3 is 1 and phi 4 is equal to 0 at x is equal to 3 by 2 for the second element. So this gives us a constraint equation that a2 is equal to a3. And when you substitute this particular constraint equation in the four equations which you have derived, represented by equation number 1, uh, what you are what you basically the mathematical concept behind this constraint equation is that you add up that you add up column number 2 and 3. So once the column number 2 and 3 are added up, you end up with four equations and three unknowns. That is four equations and three columns. And obviously, this is a rectangular matrix, so it is not going to be a symmetrical matrix. So the all the advantages of symmetry are lost. Also notice that the implementation of the constraint equation does not affect the terms on the right hand side of the equality sign. And in fact, since symmetry is a very important concept in finite element method, all the stiffness matrix which we are going to derive and the global stiffness matrix which we are going to get after the assembly process has been carried out, all these matrices are going to be symmetrical because of some advantages which we are going to discuss in the previous classes, in the future classes. So to obtain this symmetry, we basically add equation number 2 and 3 also. So when you add equation number 2 and 3, what you get on the left hand side is a matrix of size 3 by 3, which obviously is a square matrix now and is a symmetrical matrix also, as can be seen in the equation on display. And the thing is that when you add equation number 2 and equation number 3, the corresponding terms on the right hand side of the equality sign, they also get added up. So the right hand side of the second equation and third equation is also getting added up. And this gives us this gives us a point which is of importance at this particular moment. The two values of flux which have been evaluated at x is equal to 3 by 2 for element number 1 and element number 2. Both these two terms are being added up on the right hand side also. And please notice that one of these fluxes appears with a positive sign, the other term appears with a negative sign. So when these two terms are going to be added up together, they basically this basically means that the that there is some amount of heat which is entering a point and there is some amount of heat which is exiting a point. And obviously for thermal equilibrium, the summation of these two is going to be zero in the case that if there is no heat source or heat sink situated at this particular point. So we are simply going to replace these two terms by zero if there is no heat source or heat sink present. But in the case if there is a heat source or a heat sink present, then the numerical value of the heat source or heat sink is going to be substituted in the right hand side. So this particular thing is depicted, is explained in the future slide. Just a moment. Over here. So the value of the heat source or heat sink is going to be substituted in the second equation, right hand side of the second equation. But if there is no heat source or heat sink present, we simply are going to substitute it zero. Also notice that on the right hand side we have two terms of heat fluxes. One has been evaluated at x is equal to 1 and the other has been evaluated at x is equal to it should have been x is equal to 2 and not x is equal to 3 by 2 as is depicted over here. So out of these two heat fluxes, the value of heat flux at x is equal to 1 is not known, but the value of the heat flux at x is equal to 3, x is equal to 2 is a known quantity. So we can substitute it in the right hand side of equation number 3. So this is the final equation. We have 0 on the right hand side of equation number 2, and we are going to substitute the boundary condition which has been supplied to us in the right hand side of equation number 3. because this term has been evaluated at x is equal to 2 and not x is equal to 3 by 2. That is a typing mistake over here. So just to summarize, we had four equations. The upper left corner consisted of stiffness terms from the right corner corresponds to the stiffness term of the second element, and there are four unknowns represented by F A1, A2, A3, and A4, and there are four terms, forcing terms that have been kept on the right hand side. And then once the continuity condition has been implemented, you end up with four equations and three unknowns. And then to have a symmetrical matrix, you add equation number 3 and equation number 2 to give you the final form of the equations that are represented by equation number 3 get for the case when the domain has been divided into two elements. And please note that the terms on the right, in the second equation, you have contributions from the two elements which are getting added up together. In the next slide, we are going to divide the domain into four elements. So we have element number 1, element number 2. Element number 1 has two nodes, node 1 and node 2, located at XA and XC. Similarly, element number 2 has two nodes, node 3 and node 4, located at XC and XD. And corresponding value of unknown are represented by A1 and A2 and A3 and A4. So we have equation representing the unknown parameter. For the first element, it is U is equal to A1 plus A2 where 1 and 2 obviously are linear expressions in X. Similarly, for element number 2, the unknown parameter is represented by U is equal to A3 plus A4 where the expressions for 3 and 4 obviously happen to be linear expressions in X. Similarly, we have the fifth equation, we have the third equation and the fourth equation, the third element and the fourth element. The third element consists of two nodes given by node 5 and node 6. Similarly, element number 4 has two nodes, node 7 and node 8. And so we have the expressions for the unknown parameter for element number 3 also. And we have the expression for the unknown parameter for element number 4 also. And please note that to simplify the calculations, all the four elements have been taken as has been taken to have a equal length, because this is going to simplify our calculations. The boundary conditions obviously remain the same. They are the values of the unknown parameter u prescribed at x is equal to 1 and the value of the flux which has been prescribed at point number 2. So as a result, we are going to get two equations for element number 1, two equations for element number 2, two equations for element number 3, and two equations for element number 4. So in total, we get eight equations corresponding to eight unknowns represented by A1, A2 till A8, and we have eight forcing terms on the right hand side. The next step is the enforcement of the continuity condition. So we have element number 1, element number 2, element number 3, and element number 4. And the Enforcement of continuity condition means that the common point between element number 1 and element number 2, which is given by xc. So for element number 1, the unknown parameter at xc should be equal to the value of the unknown parameter at xc. This is for element number 2. Similarly, the common point between element number 2 and element number 3 is at point xd. So at xd, the value of the unknown parameter is going to be same. Now these continuity conditions, when implemented in trial functions, gives us the three constraints equations given by a2 is equal to a3, a4 is equal to a5, and a6 is equal to a7. And this means that when these three constraint equations are going to be implemented in the eight equations which we have recently developed, so when the constraint equation a2 is equal to a3 is implemented, we basically are going to add column number 2 and 3. Similarly, for the second constraint equation, a4 is equal to a5, we are going to add column 4 and 5. Similarly, when a6 is equal to a7, we are going to add column number 6 and 7. This is going to give us 8 equations with 5 unknowns, which means that the matrix which we get is of size 8 rows and 5 columns, which basically is not a symmetrical matrix. Now, to make this particular rectangular matrix a square matrix and to gain the advantages of symmetry, we are going to add up corresponding rows also, which means that since we are adding column number 2 and 3, we are going to add row number 2 and 3 also. Similarly, since we are adding column number 4 and 5, we are going to add row number 4 and 5 also. And similarly, rows number 6 and 7 are also going to be added up, which is going to give us 5 equations with 5 unknowns, which means a matrix of size 5 into 5 is going to be obtained. And this basically is going to be symmetrical also. Now coming to the actual matrix, this is on display. So there are 5 rows, 5 columns. That is, the global stiffness matrix is of size 5 by 5. And in this particular matrix, please notice that in the second row, second column, there are the contributions from the first and the second element, they have been added up together. This is because the first and the second element have node number 2 in column. Therefore, in the global stiffness matrix, the contributions of first and the second element are getting added up together in second row and second column. Similarly, talking in terms of element number 2 and element number 3, element number 2 and element number 3 is going to have node number 3 in column 3 in common. Therefore, the contributions of element number 2 and element number 3 are going to be added up together in third row, third column. Similarly, row number 4 and column number 4 has contributions from the third and the fourth element added up together. And similar contributions are going to be added up together in the terms on the right hand side also. The second row, second equation in the right has forcing terms added up from the first and the second element. And similarly, the third equation on the right has forcing terms added up together from the second and the third element. And similarly, the fourth equation on the right has forcing terms added up together from the third and the fourth element. So this is the final expression which you get. And in the next slide, we are going to expand the boundary terms which is present on the right hand side of the equation. The force existing on the right hand side consists of two terms. One of them is the interior loading, and the other is the term which happens to be the boundary load, boundary term, which is the flux which has been evaluated at the endpoints. So in the next slide, we are going to expand the flux terms evaluated at the endpoints. So these are the corresponding fluxes existing on the right hand side of the five equations. Please notice that in the second equation, you have the two fluxes from element number 1 and element number 2. Both of them have been evaluated at a same point given by xc. Similarly, in the third equation, the fluxes have been evaluated at xd, and in the fourth equation, the flux has been evaluated at xe. And for example, if we talk about the second element, both the fluxes have been evaluated at a same point xc, obviously, but one of the fluxes is with a positive sign, the other flux is with a negative sign, and if there is no heat source or heat sink present, we simply are going to replace the terms in the second equation by 0. Similarly, the terms in the third equation are also going to be replaced by 0. And similarly, the fourth term is also going to be replaced by 0 if we do not have any source, heat source, or sink located at these three values. Otherwise, the value of the heat source is going to be substituted at this particular point. Now, in the next slide, we are going to develop a very important concept, which in fact depends upon the application of continuity, that is the assembly rule. And this we are going to uh, discuss in the another lecture, which we are going to schedule somewhere in the evening today. So we conclude the lecture at this particular point. If you have any query, you may kindly uh, communicate the queries to me on the WhatsApp group, or you may have a you may call me on phone. So this is where we conclude for the time being. Thank you.